I have a handout, but I'm going to give them at the end of the class about this particular lecture, okay? So it's not too complicated since I'm not using the PowerPoint. I think you'll be able to follow. What I want to talk about today is what's called transmission matrix. And this you will find eventually very useful in all sorts of acoustics, noise, computations, transmission matrix, or matrices. It's not very common to find it in textbooks, so it would be good to have taken good notes. Now, what we mean by transmission matrix is, if you consider a medium where sound is propagating back and forth, and let's just consider arbitrarily two boundaries in which sound is traveling back and forth. And then we call, let's say, pressure and particle velocity P1 and U1 at one point, and pressure and particle velocity P2, U2 at the other point. What we want to find out is some sort of a universal relationship between pressure and velocity at one point and pressure and velocity at the other point. In general, we can write the field as e to the ikx, just for normal incident plane waves. Of course, it's harmonic and understood, but I'm just dropping that for ease. And the particle velocity is written as a e minus ikx. Okay. So far, it's clear enough. Okay. Now, what I want to use now is boundary conditions. At x equals 0, okay, we say, what is P1? Yes, yes, speak up, it's okay. Exactly, yeah. I mean, don't hesitate, because you're going to get up on the board next week and start talking. So speak up. A plus B. And velocity is, yes? A minus B, thank you. Okay, now we go to x equals L. There, the pressure is okay, very easy, and the particle velocity is similarly okay. Now, what I want to do is eliminate A and B between these, so you have a direct relationship between pressure and velocity in one spot and pressure and velocity at the other spot. You see what I'm getting at? You eliminate A and B completely now. And to do that, you can just substitute, but let me just write. Okay. Now, if we substitute for the values of A and B for P1, actually right up here, substituting for A and B in the equations for the pressure and particle velocity at x0, that's P1. Okay, just trying to okay, I skipped a couple of steps here. But if you substitute these two values into P1, do you want me to do this? I think you can handle this, yeah. And so what we have now is relationship between P1U1 and P2U2. So what I want to do is write it in matrix form. In a color. Okay, and okay, and this is a very simple matrix relationship between two positions for a plane wave.
Does it make our job easier for the midterm question? The first one?
The first one, let me see. Yes, it does, actually. In fact, as I show you more and more examples, what is very interesting with this is just a transmission matrix for a distance, a gap in space, okay? But we will write transmission matrix for a plate. for instance, okay, when sound comes from one side to the other one, you can have a transmission matrix for a plate for any number of different things. Then what you do is to find how sound is transmitted from one to the other end when there are all kinds of different things. You know, there's a gap, a plate, a gap, a membrane, etc. You put the matrices side by side, multiply them, and you have it. And this is therefore a very, very powerful method. And I mentioned last time it was actually developed by Professor Ingard. And it's not published in very many places. So in any case, so just to see some of the things that we're able to do with it, for instance, we rewrite pressure. You can see here it's T11 P2 minus, or actually plus, T12 rho CU2. And as you can see, these are our acoustic states and the matrix elements next to it. Now, if we want to express the impedance in terms of a matrix, let's say Z1, then we divide them. P1 divided by rho CU1. And then what we have here is if we further try and simplify this by dividing both sides by rho CU2, what you have then is impedance at both ends in terms of the transfer matrix elements. Of course, let me just have your attention for a second. If you have just outgoing waves from this, from XL forward, then Z2 will be equal to 1. And this is, you end up with T11, T12 divided by 2,1 and 2,2. Now, what is the determinant of the transmission matrix in this case? Can you tell? Sorry? I'm asking you. Is it 1? Yes, it is 1. So now this is also very important. It also indicates that it's not adding anything to the system. It's not an external energy source. So it has a determinant that's equal to 1. It's just a transmission matrix relates one end to the other end. Okay? So you can see now is a very simple relationship between the impedances at two ends through the matrix. How about a reflection coefficient? Okay? Pressure reflection coefficient. Okay, and reflected pressure divided by incident pressure. So once again, I'm going to write this up there so save some space. Okay. We know the P1, okay, is incident and reflected pressures, and we can write it in terms of the pressure reflection coefficient. Similarly, for particle velocity, we have now, impedance was a ratio of these two. So the impedance is a ratio of 1 plus the reflection coefficient divided by 1 minus the reflection coefficient. And from here, we can express the reflection coefficient in terms of impedance Z1, right? So, and that will be now. Let me clean this. We already are able to express the impedance in terms of transmission matrix. So if we substitute for Z1, we can now express okay, let's take a quick look at this and see what this expression is telling us. Okay? Sound waves are coming in. They are reflected back and transmitted forward. And the impedance is expressed as Z1 and Z2 at these spots. What it tells us is using the transmission matrix between these two spots, and if you know the impedance expression at the other end, you can get the coefficient of reflection, exactly like your problem, okay? Very simple. Whether these are complex or not, it doesn't really matter. This is the expression, very, very straightforward. And if the impedance here for plane waves is equal to 1, okay? If outgoing waves have an impedance P2 is equal to rho CU2, that's for a plane wave, then you have simply okay. Make sure you use these correctly. Okay, the difference between them is Z2 is equal to 1 on this. But you need to make sure that you don't make a mistake in these. Now, let's look at the next natural extension of it. That would be the transmission pressure transmission coefficient. Any questions on these? Okay, pressure transmission. Questions? No? Okay. Once again, we write for pressure here, okay, P1 and related to and oops. Yes. Just a moment here. Yes, okay. Okay. Just an inverse impedance, divide both sides by P2. So we have a direct relationship between pressure 1 and pressure 2. Of course, pressure 2 is, in this case, the transmitted sound. So what we have is transmission coefficient as PT over PI. Let's see, I want to do one more thing here. P1 is, just to remind you, is also PI 1 plus R. Okay? So, so what we have is PT PI 1 plus R divided by T11 plus T12. C2. Okay. All right. If we substitute these, 1 plus R, let me see. Let's keep a general view of this. I'll just do it. Okay, we have some cancellations. Let me just erase this up here for a second. Okay, one more time, and finally we have a clear expression for the transmission coefficient as all right. Now, again, for outgoing waves, outgoing plane waves, normal incidence, pressure is equal to acoustic impedance times particle velocity. It means Z2 is equal to 1, and tau takes a familiar shape. That there's a mistake here. 1, 2. Sorry, this is 1, 2. Okay. And these numbers, the values might change, but the shape of the transmission matrix is always the same. Now, something that you have not yet really dealt with, and that is the absorption coefficient. What would it be? What is an absorption coefficient in a system like this? Absorption coefficient is the portion of the sound wave that is not recoverable, that turns into heat, basically. So it usually happens when you have a complex impedance. So it will be the difference between reflected, incident, and reflected and transmitted. So that's what's lost. So let me just quickly describe the expression for it. Absorption coefficient. But this is, in this case, for power and plane waves, just a simplified expression, and Z2. And absorption coefficient is, power absorption coefficient is the difference, reflection and transmission. Okay? If there's no absorption of course, this would be zero, meaning incident power would be equal to what's reflected and what's transmitted. And if we have, what was reflection? Okay. And again, this is the power reflection coefficient in terms of the transition matrices. Now, yes.
How do we derive the absorption coefficient?
This is the when you have, let's say, a surface, okay. Pressure is incident and some pressure is reflected and some pressure is transmitted. Now, if you consider these in terms of power, okay, and normalize them with respect to it, so reflection is basically for plane waves, power reflection coefficient. And transmission coefficient is very similar to it. Okay. Now, if energy were conserved, okay, they would add up to 1 if energy is conserved. But if energy is not conserved, meaning there's absorption, the difference will be the absorbed amount, sound absorbed by the wall, for example. Okay? Make sense? Yes.
Only at the interface?
For this, what we're saying is sound. What is the absorbed sound? Not necessarily defined at the interface, but the absorbed sound energy as it goes through, let's say in this case, through this body. Okay? And you'll see that for Z2, where it's just transmitting, and if you do not have any, let's say, impedances that's represented by complex expressions, which suggests that there's absorption. If you do not have any mechanisms for absorption, that will become zero. Okay? And what does that mean? That means in here, in these expressions, you need to have expressions that will make it such that their numbers will add up to less than 1. If not, there's no absorption. I think we will have some examples that demonstrate these. Okay? Any other questions? Yeah. Now, a moment ago, we said, okay, well, we are able to represent the pressure and velocity state at one point to pressure and velocity state at another. Okay. Well, what happens if we're interested in the other direction? What does your logic tell you? What should happen? Yes. I think that makes very good sense. So let's call this the reversal of direction. Reversal of direction. And in this case, what we want to do is express the values at XL in terms of the values at X1, but in this case, the transmission matrix, you take inverse of it. Okay? It's as straightforward as you can get. And what is the inverse of a transmission matrix or a matrix? Do you know? Basically, you divide it by its determinant and switch the, well, for 2 by 2 matrix. Yeah. Okay, that would be the determinant is, of course, and if, let's see, then you can more explicitly write the expression for P2 as 1 over D This is the essence of transmission matrix. And one can develop transmission matrices for any acoustic medium. And let's see if we can do that. I'm going to ask you to try to do one for a membrane. See, give it a try. What we're saying is, let me clean this. Okay, we'll see transmission matrix for a membrane. Okay, we have a membrane here. And sound is incident. Sound will be reflected. Sound will be transmitted. Okay, what is the difference, essential difference between a membrane and a plate? Do you know? No, it has a mass, but it doesn't have something else that plate has. See? What?
Length.
Length? No, it has to have a length and thickness, but something else that. Think about a plate versus a membrane. What's the difference, just physically? Stiffness. Okay. A plate will have stiffness like a beam, but a membrane will not have that. Just keep that in mind. So, when you think about the impedance of a physical object, you have what? Mass. Stiffness. Come on. What's an impedance? Force divided by velocity, okay? What are impeding the force from gaining velocity? It's mass, you have to push it. It's stiffness, same thing. And one more thing. Damping, exactly. Assume now that you don't have stiffness or you don't have damping. Just simply what would happen. See if you can just model this very quickly. See if you can get a transmission matrix expression for a membrane. You know everything you need to know to do this, okay? Let me clean this up. Do you have it?
No, I didn't understand what you just assumed about membrane.
That membrane only has a mass. It doesn't have a stiffness, it doesn't have damping. So you just have a very, thin material, okay? And then sound is transmitted through it. So how is the sound field affected by that? And we want to be able to, just like the layer, but now instead of a layer, you have a membrane. How would you write the transmission matrix for it? Because we do use membranes in acoustics, like curtains, for example. Okay? And you need to know how to calculate it. So this is a transmission matrix. What are you trying to do? You're trying to relate pressure and particle velocity on one side to pressure and particle velocity on the other side. As simple as that. Okay? Think about it and see what you can do. Write down the usual. Okay? This is the only way you're going to learn these things. Okay? Try.
Same properties on both sides.
Same properties. Yes. Very good. Yes. Yes. Just in air, you have a membrane, thin membrane.
Relates the pressure and the particle velocity of one side to another.
Exactly. Excellent. Okay. So shall we say this is one side? Okay. P1 rho C U1. And then this is the other side. And we want to relate these entities to one another. Well, does it have to be anywhere? It can be. Okay? So our goal is to drive a nice transmission matrix that relates the pressures and the particle velocities. What do we know about the system? What are some of the, we have to write down something. What do we know?
We can write pressure distribution.
Pressure distribution. Okay, tell me, what is the pressure distribution? I'm going to write it on, over here.
P1 equals to
P equals what?
a constant A, then e to the power I, parentheses, Wt minus kx,
Omega t. Okay.
plus, no, parentheses, another constant B, plus the negative of it, I, no, okay, we can do that. Omega t plus kx.
Okay.
The difference with the P2, there will be no reflections in P2, only transmission.
So you'll have something like this, is what you're saying, right? Okay, how does that help? What do we do next? You don't agree. Amrullah.
I think P2 must be the negative side, P3 minus kx, because it uses the yes.
P2 where?
Minus kx. Minus,
Really? It's going back?
because it uses the different directions. If you look at the equation 1,
Okay, fair enough. Then what do we do with these? Now this is correct. This is the pressure distribution. Now what?
I think we can assume that pressures and velocities must be continuous at membrane.
Pressures and velocities must be continuous at the membrane. Is that right? Okay, so P1 and must, what's that? What's that?
He said he tried this material.
So you're sending us in the wrong direction. Okay. But, well, let's talk about this continuous business. Velocity, let's take velocity. It's continuous, you say, right? Think about this. Is the membrane moving? So the air must move with it. Okay? That makes sense? Okay. U1 is equal to U2 at, let's call this x0.
May I ask something?
Sure.
So this time maybe the pressure is not continuous because it must move, membrane must move.
And these are the mechanical engineers. Okay? Exactly. You see, there's a, that's right. Exactly. Okay? So what does it, if there's a mass and if you have pressure coming from one side, if it has to move it, then what do you have? How could you express that expression? Okay? That's an excellent start. What do we do with that? What does it say? Go ahead.
We take the difference.
Mm-hmm.
Surface area is the same.
Yes. So the pressure difference must cause acceleration. Exactly. Okay? So if we call the displacement of this membrane as eta, then you have, let's see, m delta eta del t. Or, yes, doesn't matter. Either way, you can express it in a number of different ways. Let me do it in the most familiar way. Okay? So it must accelerate it. And what is m? These are details, but important. They get you in trouble. What is m?
What is?
M.
Mass of the membrane.
Is it the mass of the membrane? Or this is pressure, mass per unit area. Okay, mass per unit area. Does that make sense? Do you follow it? Because it's pressure. Pressure is force per unit area. So if it's mass per unit area, how would you find that? That's equal to density times its thickness. This is detail, but when you solve problems, they get you in trouble. Okay, so we have one relationship here, and then we said particle velocity must be the same on both sides. How does that help us? How does it help us? Why does it have to be the same on both sides? They don't even touch each other. Because they're equal to the membrane velocity. They can't separate, okay? All right. See, it's very simple, actually, when you think about it. So if we go back and let's see. You can see now that we don't necessarily need these, the distributions, because we're always working right at the surface, and we're interested in total pressure on one side, total pressure on the other side, irrespective of what's reflected, what's incident, and so on. And we can find those once we have the transmission matrix, because we know what they should be in terms of the transmission matrix elements. Let's, okay. So if I go back here, say, P2 minus P1 is equal to m del eta del t. and that is I omega m eta dot. Okay, but we also know that eta dot is equal to u1 and that's equal to u2. Now you know the relationships that we need. How would you put them together? Let's see. Actually, can I just change this because I think this makes more sense for the positive direction. Change it here to P2, P1. Okay. All right. Using this relationship, P1, P2, now eta is already equal to U1, right? Or U2, sorry. This is what I want to do. And how is it related to P2? Particle velocity. It is not. But it is equal to right? Now, to make sure I have rho C, now one is able to okay. And that would be the transmission matrix for a membrane. What is the reflection coefficient? Can you quickly determine what that is? Pressure reflection coefficient. I'm sorry, say again? No, what is pressure reflection coefficient? Go ahead, answer again, please.
It's T1, 2, minus I omega m equals C, minus 1.
No. Remember, we had a reflection coefficient in terms of matrix elements. And let's say in this case for a plane wave that's going out for which Z2 is equal to 1. And that one was I think this is the case, okay? If you now substitute the values for it, 1 minus I omega m over rho C, 0 minus 1, and then you sum all of these, 2 minus I omega m over rho C. Yeah. Does that make sense? This is the pressure reflection coefficient. What is the power reflection coefficient? Very quickly. Just write it down. Power reflection coefficient. These are all plane waves. What is the power reflection coefficient? How would you calculate it? Well, okay, give me the values. It's a complex number, so you need to know how to very quickly get the amplitude of a complex number, okay? Okay, you have to be familiar with these. But here's an interesting, write this down and then let me tell you something interesting about this. Go ahead.
I think the numerator has to square.
Yes, it does. Thank you. Okay. Okay. What does all this tell you? Okay, we always talk about equations, expressions, telling you a story. When you look at this, of course, what is important is the top part, the numerator. What is the numerator telling us? What does this number tell us? Take a quick look at it. What does it say? It's omega times m divided by rho c. Rho c is what? What kind of specific acoustic impedance of the fluid medium? What's omega m? What is it called? Do you remember? You don't remember? Think about this, right here.
Damping?
No. No damping. What is the damping? There's no damping. Omega is not damping, m is a mass, omega is frequency, so it's not damping. But always go back. Okay, this is a force-like quantity, pressure. Okay, you have mass, you have omega m, and what is this? Well, velocity, at a dot. It's velocity. So, is what? What would this be? No. Impedance. Force divided by velocity. Remember, membrane does not have stiffness. Okay? Force divided by velocity is impedance. And what kind of impedance? This is called inertial impedance. Okay? Meaning mass impedance. It's a mass impedance. Every time you see I omega m, it's a mass impedance. Now, we look at here, we say, what is this the ratio of now? Mass impedance per unit area to specific acoustic impedance of the fluid. Now, what do you think this ratio is? Is it large, small? Depends on frequency. What else does it depend on?
Medium.
Exactly. You can have a piece of paper, which is a membrane, well, let's say plastic, and put it in water. Of course, it's going to have very little. This ratio will be very small, depending on the frequency. Now, this is an interesting topic that you bring up, frequency. Look at this. At low frequencies, membrane impedance is very, very small. What does that mean? What does it mean, even in air? If you have very, very low frequencies, an ordinary membrane, what does this mean?
Close to zero.
Right, and that means very low frequencies, membrane will not reflect, sound will go through it. That's very important. It's one of the fundamental issues in noise control. Low frequency sounds are very difficult to control. Okay? Therefore, for very low frequencies, the only thing you can do is increase the mass. Okay? For quiet rooms, very, very high values for mass. One. Secondly, the other thing is, let's go back to this impedance for a moment. Impedance increases with both mass, of course, but for a given mass, with frequency. So something will be more difficult to move the higher the frequency. Okay? At low frequencies, you can move something easily. Okay? But at high frequencies, it's difficult to really generate that. So if you, in fact, do a power analysis, of course, that will go with increase with frequency quadratically. Okay? So when you look at these, now you know what we're talking about, okay, in terms of what this means. At extremely high frequencies, we said at low frequencies, it's almost zero. At hugely high frequencies, what happens?
It's almost one.
Say again?
It's almost one.
Exactly. All the sound goes through, okay, much larger than this. So what we mean in acoustics always, large, small is compared to something. In this case, if omega over rho c is much larger than 2, or omega m is much larger than 2 rho c, then sound will go straight through the membrane. Okay, there's no, I'm sorry, yes, it will, sorry, it will come back, yes. Why again? At high frequencies, excuse me, yes, at high frequencies, impedance is very, very high. It can't move it. Okay? I think you learned some good physical things and a good approach to transmission matrix and so on. Now, of course, this is a simple transmission matrix. We did not do it for oblique angles. We'll do it next time. Okay? Maybe one of you will do it. But it's you'll see that it's no different than what we have done before. And now you can have two membranes, a space between them, you know how to solve it. Get 3 matrices, multiply them, or let the computer do the job for you. Okay? Any questions? You understand the essence of transmission matrix and some of what equations should tell you. Okay, so that when you solve your problems, you don't make mistakes. People talk about, oh, at high frequencies this happens, low frequencies that happens. These are evidences of those. Questions? Okay. Thank you. See you next time.